Hello again. This is section 8.2, graphs of polar equations. So if you remember in section 8.1, what we looked at were actual polar coordinates and how we could actually convert between both rectangular and polar coordinates, and then also take some equations and convert them between one form and the other. In this section, we're actually going to start to look at the graphs of some of those polar equations that we started looking at back in section 8.1. So if you notice here, I've got the rectangular coordinate grid, our normal X and Y axis. And then beside that, I've got the polar coordinate grid. Notice here that the polar coordinate grid is a bunch of circles. We call those concentric because they have the same center and they just get larger as you go out. And if you remember back in 8.1, I mentioned, we're talking about now having an R value that could vary, right? And so that R value could be 1, 2, 3, 4, 5, 6, as you see there on that graph. And then we're just going to use what was our unit circle values to figure out where that point is located now around that circle. Okay, so rather than just having one circle with a radius of 1 like we did with our unit circle, now we have all of these circles with different radii, but our angles are still going to be in the same location. And so to plot these points, we just have all of these bigger and bigger circles that kind of work their way out. All right, so here's our polar grid. It says we want to sketch the graph of the equation r equals 3, and we want to write this in our rectangular form. Okay, so we're going to do both. We're going to work with what we did in 8.1, write it in rectangular form, but then we're also going to try to sketch the graph. Now, notice here, there is no theta in this equation, which means that theta could be virtually anything, right? So our r value just has to be 3. So I'm going to find an r value of 3. So I look here and I say, all right, let's count out 3 circles. 1, 2, 3. And I'm going to put a point right here with that radius of 3. And like I said, because there is no theta, theta could be anything. And so therefore, I'm going to have a point at every theta value along that r value now. And so if you notice here, if I do that, if that r value is always 3 and theta can be anything, when I connect these now, I end up with a circle that has a radius of 3. Okay, and so that would be the graph of the equation, the polar equation, r equals 3. Now, the second part of this says we want to put this into rectangular form. So if you remember those formulas that we looked at in the previous section, we have one that has an r squared in it, and we can convert that into x and y. And so what I'm going to do here is I'm going to square both sides of this equation to get r squared equals 3 squared. Because I know that r squared from the previous section is equal to x squared plus y squared, and then 3 squared gives us 9. And so our equation in rectangular form this time is going to be x squared plus y squared equals 9. And if you remember back to pre-calculus, x squared plus y squared equals some value is the equation of a circle. Okay, and the center of that circle should be at 0, 0. And the radius is just the square root of the number that we have there. The square root of 9 is 3. And that's why we end up with a circle centered at 0, 0 with a radius of 3 this time. All right, now this next one, we have theta equals pi over 3. Again, we want to put it in rectangular form, and we want to sketch the graph. So we'll start with the graph, and then we'll change it over to rectangular form to see how that compares to the graph that we got. Well, this time there is no r value. So r could be anything it wants to be, but I know my theta value has to be pi over 3. So I'm going to locate pi over 3, which is right here. And I'm going to put points at every single r value along that pi over 3 line. So we have a point here, 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 right? Because that radius could be anything. So we're going to get something like this. Now, what we also have to remember is if we have negative r values, those negative r values get reflected over the pole. So technically, if I have negative r values, they're going to get reflected down here now. And so we're going to get all of these points for negative r values along that 4 pi over 3 part. So basically what we end up with now is a line goes right through the origin or the pole, and it's going to look something like this. Now, this time we want to put this in rectangular form. The only one that I've got that has like a theta in it would be the tangent theta equals y over x. So what I'm going to do here is take the tangent of both sides of this equation. So I'm going to write tangent theta equals tangent pi over 3. Well, tangent theta is equal to y over x, and the tangent of pi over 3 is square root of 3. Okay, so there's our equation in rectangular form. Now, a form that you're probably more familiar with would be if I get it y by itself, right? So I'm going to solve for y here. I'm just going to multiply both sides by x. So we get y equals square root of 3 times x. So basically what this tells us is we have a linear equation where square root of 3 is our slope, and then the y-intercept, the b value, is just a 0, right? And so square root of 3 is our slope, and that's what gives us this line along the pi over 3 line. And then we just have a line that goes through the origin. That's where the y-intercept comes in. So in general, if you just have an r equals some value, that's going to give you a circle. If you have a theta equals some value, it's going to give you a straight line. All right, now let's start looking at some more interesting ones. So this time we've got r equals 2 sine theta. Now this time they don't ask us to put it in rectangular form, so we're just going to try to graph this one. In this case, the best way to graph these without some kind of graphing device is going to be to actually create a table of values. Okay, so that's exactly what I'm going to do first. I'm going to create a theta column. I'm going to create an r column. Now, the theta values that we choose, I'm going to try to choose values that we're familiar with. So the 0, pi over 6, pi over 4, pi over 3. Those values are the ones I'm going to test here. So we'll start with theta equals 0. And we're substituting that into our r equals 2 sine theta equation to figure out what r is going to be equal to. Well, if I do that, sine of 0 is 0. 2 times 0 is still 0. So my r value there is going to be 0. Now I'm going to do pi over 6. If we do sine of pi over 6, that should give us 1/2. 1/2 times 2 should give us 1. So my r value there is going to be 1. Okay, then we'll do pi over 4. Sine of pi over 4, square root of 2 over 2. If I multiply that by 2, that's just going to give us square root of 2. And then pi over 3. Sine at pi over 3 is square root of 3 over 2. Multiply that by 2. We should just get square root of 3. And then I'm going to do pi over 2 next. Sine at pi over 2, that should be 1. 2 times 1 is 2. So we get an r value of 2. All right, now I'm going to go ahead and start plotting these values. We're not done yet because I'm actually going to have to go all the way around my circle and make sure we hit every single value that we've got here. Okay, but I'm going to start plotting these points. Well, a theta value of 0 and an r value of 0 is going to be right there at the pole, at the origin. Okay, now my next one, we have an r value of 1. We have a theta value of pi over 6. So I need to go out 1 along my circles. And I'm going to go around to pi over 6. And so that's going to give us a point right here. So on the pi over 6 with a radius of 1. Next, we have pi over 4 square root of 2. So we're going to have to approximate this one for our radius, right? So square root of 2 is somewhere between 1 and 2, closer to the 1. And then we're going to go around to pi over 4. So that's going to give us a point right here. Square root of 3, also somewhere between 1 and 2, this time closer to the 2. We're going to go around to pi over 3. So we should have a point right here. And then finally at pi over 2, our radius is 2. So we're going to be right on that second circle at pi over 2. So we're going to get something that looks like this. All right, now I'm going to extend my table. I'm going to keep going. Let's look at our values from the second quadrant now. So 2 pi over 3 would be next. If I do that, we're going to get sine of 2 pi over 3 is square root of 3 over 2. We multiply that by 2. It's going to give us square root of 3. Then we'll do 3 pi over 4. Sine of 3 pi over 4 is square root of 2 over 2. Multiply that by 2, we get square root of 2. 5 pi over 6. Sine of that is 1/2 times 2 is 1. And then pi, sine of pi is 0 times 2 is 0. So notice here, we're basically just getting those same values we got before, just in reversed order now. So 2 pi over 3, square root of 3. I'm going to be somewhere between 1 and 2, closer to the 2 at 2 pi over 3. So that's right here. Square root of 2, again, somewhere between 1 and 2. A little bit closer to the 1, though. We have a point here. At 5 pi over 6, our radius is 1. That's going to be here. And then at pi, our radius is 0. Anytime the radius is 0, you're going to be at the pole because we have no radius at all. Okay, and so here, we're back to the pole. Now, it's important that we connect these points in the order that we've plotted them. So notice here, I started with 0, went to pi over 6, then pi over 4, right? I'm putting them in numerical order. And so when I connect these now, we're going to get something that looks like this. Now, I need to keep going just to see what's going to happen if I go into the third and fourth quadrants now. So I'm going to keep going with my thetas and my r's. Okay, so my next point, working into that third quadrant, 7 pi over 6. So the sine at 7 pi over 6, because we're in the third quadrant now, is going to be a negative 1/2. 2 times negative 1/2 should give us negative 1. Then we've got 5 pi over 4. Again, sine is negative in that quadrant, so we're going to get negative square root of 2 over 2 times 2, which is negative square root of 2. 4 pi over 3. Again, we're going to get a negative value, so we're going to get negative square root of 3. And then at 3 pi over 2, we should get negative 2. Now, remember with our negative r values, what that means is we're going to end up reflecting over the pole. So if I come out here and I look at 7 pi over 6, that radius would have been 1. So I'm just going to put a point right here just to show you. But then if we reflect it over the pole, it actually gives us the point that we already have up here in the first quadrant. So we've already plotted that one. Okay. Now, 5 pi over 4, negative square root of 2, same thing. I'm going to have a point somewhere in here. But if I reflect that over the pole, now it gives me this point, which again, we've already plotted. And the same thing is going to be true for all of these negative r values now. As I work my way around, once they reflect over the pole, I'm just hitting those same points that I've already plotted that were between 0 and pi. So there's no real reason to continue on because it's going to give us all the same points that we've already got. And so this right here is our complete graph now. basically a circle that's no longer centered at the origin or the pole. It's actually shifted up now. Now, there's not going to be any graphing on a test or an exam, okay, but I do want you to at least see these graphs to understand, what they look like. I'm going to give you a chart at the very end that kind of shows you a general, if the equation's in this form, then this is the shape of the graph, that kind of thing. And some of these graphs are just really interesting, right? And so it gives us ways to plot things that would otherwise not be functions. Polar coordinates give us a good way to do that. All right, so our next one here, we've got 2 plus 2 cosine theta. Again, we don't need to get this in rectangular form. We just need to graph it. So I'm going to create a table of values to try to do that. We'll do our thetas and our r's. All right, so if we start with 0, this time cosine of 0 is 1. So then we have 2 times 1 is 2, plus 2 should give us 4. And we'll do pi over 6. Cosine of pi over 6 is square root of 3 over 2. And so when we do that, that's going to be 2 times that is square root of 3 plus 2. We get 2 plus the square root of 3. And again, we're going to have to approximate these, right? So if you want to go ahead and get decimals for these values, that's perfectly fine also. So feel free to use a calculator on these. Pi over 4. Cosine of that, square root of 2 over 2. Multiply that by 2, we get square root of 2 plus 2. So 2 plus the square root of 2. We'll do pi over 3. Cosine pi over 3 is 1/2 times 2 is 1 plus 2 is 3. And then we'll look at pi over 2. Cosine pi over 2 is 0 times 2 is still 0 plus 2 is 2. Okay, so again, I'm going to go ahead and get some decimal values for those square roots. So 2 plus square root of 3 gives us about 3.7. And 2 plus square root of 2 is going to give us 3.4. Okay. All right, so if we start plotting these values, we have a theta value of 0, so that's right along that 0 degree line. Radius is 4, so I'm going to go out 4. We're going to have a point right here. Okay, next, we're going to go around to pi over 6 with a radius of 3.7, so slightly less than the 4. Should give us a point right in here. Pi over 4, we're somewhere between 3 and 4, closer to the 3, so right in here. Pi over 3, our radius is exactly 3, so we're going to be right on that circle. And at pi over 2, our radius is 2, so we're going to be right on that circle. Okay. All right, I'm going to keep going. So 2 pi over 3 is next. Now remember, in the second quadrant, cosine is going to be negative, right? And so cosine at 2 pi over 3, that should give us negative 1/2. That's 2 times negative 1/2 is negative 1, plus 2 should give us 1. And then we'll do 3 pi over 4. And I'm going to start just putting these in the calculator and getting decimal values just because I know we're going to need the decimals anyway. So if we do 2 plus 2 cosine 3 pi over 4, it's going to give us approximately 0.58. So I'm just going to round that to 0.6. 2 plus 2 cosine of the next value is going to be 5 pi over 6. Gives us about 0.3. And then we'll do pi. And that should give us 0. So again, if I continue on here, 2 pi over 3, radius is 1. So along that line, we need a radius of 1. So that's going to be right here. 3 pi over 4, 0.6. So we're somewhere between 0 and 1, a little bit closer to the 1. Somewhere in here. At 5 pi over 6, we hit 0.3. So we're getting really close in here now. And then finally, again, we said anytime the radius is 0, we're going to be at the pole because we don't have any radius at all. And so we're going to get a point right there. So I'm going to go ahead and connect what we have so far. So notice here, we basically have this curve. Starts out here at 4, and gradually gets smaller and smaller as I work my way into 0. Now, again, we still need to keep going because I need to see if the points beyond that are going to give me the same points we already have or possibly new points, right? So I'm going to actually erase what I have over here so I have space to do some new values, and then we'll plot those. Right, so I'm working on my theta values from the third quadrant next. So we're going to start with 7 pi over 6. Again, I'm just going to use a calculator since I know I'm going to need decimals. So this is going to give us about 0.3. 5 pi over 4. Gives us 0.6 again. 4 pi over 3. Is 1, and 3 pi over 2 gives us 2. And then we'll keep going. So I'm going to go into my fourth quadrant. So 5 pi over 3 is next. It's going to give us 3. 7 pi over 4. 3.4. And you may notice that we're starting to repeat some of those same values that we had before, but this actually isn't going to give us the exact same points we had. So now we get 3.7. And then back to 2 pi should give us 4. Okay. All right, so let's plot these points now so we can see what's going on. So 7 pi over 6, we got 0.3. So let's find 7 pi over 6. And we have 0.3, which again is really close to the pole. 5 pi over 4, we get 0.6, so just slightly bigger. 4 pi over 3, we're finally out to 1. So that's right here. 3 pi over 2, our radius is 2. So we're here. 7 pi over 4, 3.4. Here. 11 pi over 6, 3.7. Here. And then finally at 2 pi, we're back where we started with a radius of 4. So again, connecting these in order. You should get something that looks like this right here. Okay. And then that is our complete graph now. We've gone all the way around our unit circle to 2 pi. And so we've hit every single point. And notice here, if you see at the top, this is what we call, sorry, that's spelled wrong. There should be an R in there. That is a cardioid, right? If you think cardiac, right, that's heart. Okay, and that's how it gets the name cardioid. It looks kind of like a heart with that little cusp that we have in the middle there. All right, so the next one we've got R equals cosine 2 theta. So I'm going to do the same thing I've been doing. I'm going to create a table of values here, starting with 0. Again, I'm just going to use my calculator as I go, just because I know I'm going to need decimal values when I do this. So if we do cosine of 2 times 0, that should just give us 1. Cosine of 2 times pi over 6 should give us 1/2. Cosine of 2 times pi over 4 is 0. Cosine of 2 times pi over 3, negative 1/2. And then cosine of 2 times pi over 2 is negative 1. Now, because I notice I'm starting to get some negative R values in here, I'm going to go ahead and plot the points that I have just to make sure it's clear the order that I'm plotting these points, okay? Because I know those negative ones are going to get reflected. I don't want to get confused about the order that I've plotted these. So I'm going to start with 0, 1. And I'm actually, just because I notice here that my values are all between negative 1 and positive 1, I'm going to make my 1 this line out here, just so it's a little bit larger and it's easier to see where the 1/2 and the negative 1/2 and things like that are. Okay. So I'm just scaling my axis, right, so that the radius of 1 is actually out here where 4 normally would be. And now pi over 6, 1/2. I'm going to go around to pi over 6. 1/2 now becomes the halfway point between 0 and 1. And so that's going to give us a point right here. And then pi over 4, 0. We said anytime the radius is 0, we get a point at the pole. Pi over 3, negative 1/2. So pi over 3, 1/2 would be here, but we have to reflect that over the pole, right? So that's going to reflect down here to 4 pi over 3. And so the actual point we want is that one down there. And then finally, pi over 2, negative 1. Again, pi over 2, 1 would be up here, but if I reflect that over the pole, it's going to be down here at 3 pi over 2. And so we're actually going to have a point down there. I'm going to start sketching this now, connect these in order. And so we get something that looks like this. All right, so let's keep going. So my next value is going to be 2 pi over 3. That gives us negative 1/2. And we'll do 3 pi over 4. Should be 0. 5 pi over 6. Is positive 1/2. And then pi is 1. So again, I'm going to go ahead and plot these points that we have so far. So at 2 pi over 3, we get negative 1/2. So 2 pi over 3 1/2 would be here. Because it's negative, though, I'm going to reflect it over the pole. And so we're actually going to have a point right here. Then we have 3 pi over 4, 0. Again, anytime you hit 0, that's going to be at the origin. 5 pi over 6, 1/2. Now we're back to a positive value. That's going to be right here. And then pi 1. Remember, our radius of 1 was out here. So we're going to get this. So again, go ahead and connect these in order. It's going to come up here like this. So far, that's what we've got. Now again, we're not done yet, right? Because we've only done through pi. We need to go all the way to 2 pi just to make sure we've hit every single possible value. So again, I'm going to get rid of this table so I've got room to do my next part. So now we're working into the third quadrant, 7 pi over 6. It's going to give us positive 1/2. And you can probably see that we're starting to get a lot of these same values over and over again. 5 pi over 4 is 0. 4 pi over 3. Negative 1/2. And 3 pi over 2 is negative 1. Okay, so again, I'm going to go ahead and get these in there, and then we'll do our final quadrant. Okay, so 7 pi over 6, 1/2 should be right here. 5 pi over 4, 0. Radius is 0. We're back to the origin. 4 pi over 3, negative 1/2. So 4 pi over 3, 1/2 would be on the 4 pi over 3, but reflecting over the pole now actually gives us a point up here at pi over 3. And then 3 pi over 2, negative 1. Again, positive 1 would give us a point down at the bottom. Reflecting it gives us a point up at the top at pi over 2. So we're actually going to have a point up here now. So if I connect these, you're going to get that. And so it's starting to come together, right? You might see what the final product is going to look like now. 5 pi over 3. We get negative 1/2. 7 pi over 4 is 0. 11 pi over 6 is positive 1/2. And 2 pi should be back to 1. So 5 pi over 3. Positive 1/2 would be along the 5 pi over 3. Because it's negative 1/2, it gets reflected up to 2 pi over 3. So we're going to have a point up here. 7 pi over 4, 0. Back to the origin. 11 pi over 6, 1/2. It's going to give us a point here. And then finally, 2 pi, we're back to 1. So it's going to look something like this. And again, you may have had some context clues up at the very top. Notice here, this is a 4-leaved rose, right? Because it kind of looks like a flower. This one specifically has 4 leaves. Okay, and so cosine of 2 theta is what will give us that graph. Okay, now the last concept from this section, we can actually test for symmetry also. Okay, so just like our x and y axis has symmetry, we also have symmetry in the polar axis. So if polar equation is unchanged, if you replace theta with negative theta, then the graph is going to be symmetric about the polar axis. Remember, the polar axis is that positive horizontal axis. And so just think along the horizontal axis, if theta replaces, if you replace that with negative theta and get the same thing you started with, then it's going to have symmetry about that axis. If the equation is unchanged, if you replace r with negative r or theta with theta plus pi, so either of those two things, then it's going to be symmetric about the pole. Okay, remember the pole being like the origin. Okay, so you're going to have origin symmetry in that case. And then finally, if the equation is unchanged, if you replace theta with pi minus theta, then the graph is symmetric about the vertical line. Sorry, let me fix this because it's not visible. So it should be pi over 2. Okay. And again, pi over 2 would be the vertical line along just that vertical axis, right? And so if you replace theta with pi minus theta and get the same equation you started with, then we have symmetry across that vertical line. Now, the reason these symmetries are useful is rather than having to substitute every single value between 0 and 2 pi, if you know up front that there is some kind of symmetry, then you might be able to limit the values that you have to plug in, right? Because if I know for sure that there's symmetry about the polar axis, well, now I just need to go from 0 to pi because I know all the values from pi to 2 pi are going to be exactly the same, right? Things like that. It saves us some time in terms of the graph. All right, so last example from this section, we want to sketch a graph of the equation 1 plus 2 cosine theta. And I'm going to do the same thing I did before, but this time, because we know about symmetry now, I'm going to test and see if maybe we have some type of symmetry. I'm going to start with the easiest one to check for, which is just replacing theta with negative theta. So I'm going to write this as r equals 1 plus 2 cosine of negative theta. Well, if you remember our even odd properties for sine, cosine, tangent, cosine is an even function, and so this is actually equal to 1 plus 2 cosine of theta. Okay, because cosine is an even function, cosine of negative theta is equal to cosine of theta. And so this right here now is the same thing we started with. So that tells me that I'm going to have symmetry about the polar axis. And so remember, the polar axis is that horizontal axis along here, right? So that means I just need to test values between 0 and pi now. And if I do that, then I know the other part of my graph is just going to be a reflection over that polar axis. So let's start going here. We're going to do our thetas and our r's. Start with 0. So we got 1 plus 2 cosine of 0. That's going to give us a radius of 3. Pi over 6. (2.7). Pi over 4. 2.4. Pi over 3 should be 2. And pi over 2 is 1. Okay. So it's up to you if you want to go ahead and plot those points. I haven't hit any negative r values yet, so I'm just going to keep going because I think I'll be able to plot everything that we've got here. So let's go to 2 pi over 3 next. That should be 0. 3 pi over 4. It's negative 0.4. 5 pi over 6. 2.6. And then we said pi is the last value we need to worry about. Oops, sorry, I messed that one up. 5 pi over 6 should actually be negative 0.7. And then pi should be -1. Okay. All right, so if we plot these points now, theta 0, r is 3. So I'm going to go out and again, yeah, this time we'll just go with the normal circles. So my third circle there is a radius of 3. Pi over 6, we get 2.7, so that's going to be slightly less than 3. Pi over 4, 2.4, so a little bit smaller than what we had previously. Pi over 3, we've got 2, so that's right on the second circle. Pi over 2, 1, right here. Then 2 pi over 3, 0. Remember, 0 automatically hits here. So I'm going to go ahead and connect these just so I don't lose track now. So we get something like this. Now, 3 pi over 4, -0.4. 3 pi over 4, 0.4 would be along the 3 pi over 4 line, but we have to reflect it. So it's actually going to be along that 7 pi over 4 line now. It's going to be right in here. I'm going to erase my little dots along the axis so we don't get those confused. 5 pi over 6, -0.7. Again, I'm reflecting 5 pi over 6 over to 11 pi over 6. And so we're going to get a point right in here. And then pi -1. Again, I'm going to reflect that. And so it goes over here at 2 pi or 0 with a radius of 1. And so this curves around, hits these points here, and then goes to there. Okay, so that's what I've got so far. But remember, we said there should be symmetry about that polar axis. So now I know exactly what the other side of this graph is going to look like. So I'm just going to reflect all of these points over the polar axis, and then I'll connect them. So this point that was at pi over 6 is now down here at 11 pi over 6. The one at pi over 4 should be at 7 pi over 4. If the pi over 3 gets reflected down to 5 pi over 3. That was right on the 2. The pi over 2 reflects to 3 pi over 2, and that was at 1. And then we have that point at the pole that stays the same. And then these smaller points that were at 3 pi over 4 and 5 pi over 6 and then reflected, those are going to be up here at pi over 6 and pi over 4. They're going to be right in here now. And so basically we end up with something, if I reflect this, looks like this now. You notice it's similar to that cardioid that we looked at before, except this time it doesn't just come to a point, right? It actually kind of loops in on itself. And so this one we call a limicon. And this comes, it's a French word, which is why you have that funny looking letter in there. Okay, but that's what we call anything that kind of loops in on itself like that. Now again, none of these things are things that you need to stress yourself, especially the terminology, right? Even the graphing, right? I just want you to be familiar with how do we plot these points, right? What do these polar coordinates actually look like if we plot them in space? So that it's not just some abstract thing where we're converting between rectangular and polar form, right? We can see that there are actually graphs of these. Your graphing calculator will graph these. Desmos will graph these, right? So play around with that if you'd like to. If you have any questions about how to do that, let me know. But again, I'm not going to spend too much time showing you those things just because I'm not going to ask for it on an assessment. Okay, now, the last slide here, you can actually see these are all the different kinds of shapes that we can form. So circles, right? We started with those. You can also see the lemicons that we just did where we have those loops, okay? If it specifically has a cusp, we call that a cardioid, right? You can see that falls within that category. Then we have our roses, okay, and you can see the different types of equations depending on whether that n value is even or odd. Tells you kind of how many leaves there are going to be on the rose itself. And then the lemniscots, we didn't look at any of those, right? They kind of look like infinity symbols, either diagonally or possibly horizontally, depending on whether it's a sine or a cosine. Okay, so those are all the interesting types of graphs that you can get with polar coordinates. And again, feel free to play around in something like Desmos and just create, different functions in there and see what happens. Because these graphs, again, give us ways that we can graph things that normally wouldn't be functions, right, where we can actually get a y equals equation. Now we have ways that we can graph some of these more interesting types of curves. All right, so that's all we've got for 8.2. Please let me know if you have any questions as you're working on that homework, and I will see you next time.